Hello everyone, welcome back to Math with Allison. Today we're continuing our series on integration, so we're going to be talking about U-substitution with indefinite integrals. So let's go ahead and dive into it. Here we have a question: why are we bringing in another variable? And the answer is because we are. And we're going to see the answer as we play it out here. So let's look at our example here. We have the integral of 2x cosine of x squared. So notice here that we have multiple variables going on here. We have this 2x on the outside, and then we have cosine of x squared right here. We don't know how to integrate this yet. And it looks very complicated, but that's why we use U-substitution. It's a trick. So usually with U-substitution, we look for something that has a derivative. So let's go ahead and take a look at our function here. If we notice this, we see an x squared, and we know that the derivative of x squared is equal to 2x. So that's what I mean. We look for something with its derivative. So this tells us what our u is going to equal. So u is a new variable we're using, and we're going to replace it. So u is equal to x squared. And the purpose of looking for its derivative is because we take the derivative of u. So we're going to go ahead and take the derivative in terms of x of both sides. So u cannot be differentiated in terms of x because they're two different variables. So I'm just going to leave that as du divided by dx, but we can take the derivative of x squared. So this is equal to 2x. So what we are wanting to solve for here, the whole purpose of this, is we want to replace this dx in the actual equation. So I'm going to go ahead and solve for it on this side. So first I'm going to multiply that dx over. So I get du is equal to 2x times dx. And now I can go ahead and divide over that 2x. So I get du divided by 2x is equal to dx. And now what we can do is we can take this whole equation and we can replace it. So let's go ahead and replace our moving parts. Here we have the integral of 2x. That did not change yet, but that cosine stays the same, and we replace that x squared with u because that's what we set it equal to. So we have a u right there. And like we said, we just solved for what dx is equal to. That is equal to du divided by 2x. So notice what happens here. We have something that cancels out. This 2x cancels out with this 2x right here. And now we have a whole new integral. We have the integral of cosine of u in terms of du. So notice here, this is going to be something that we can actually integrate. And the best part is that all the variables match. We have the integral of a function in terms of u in terms of du. So let's go ahead and actually take this antiderivative. This is equal to sine of u plus some constant c. But I don't want that u to stay there because we are originally integrating in terms of x. So what I'm going to do is replace that u with what it was originally equal to. So u is equal to x squared. And now we have our final solution. So now here we can see the purpose of using U-substitution, and it's because we're doing chain rule backwards. Let's go ahead and check our answer. In order to do that, we're going to take the derivative of our answer. So when we do that, we're going to have to set up chain rules. So we have the derivative of sine is equal to cosine. Our inside stays the same. And then we multiply by the derivative of the inside. So it's 2x. And then that plus c goes to 0. So this is how we get 2x cosine of x squared, which is what we're originally integrating right here. So the U-substitution is chain rule backwards. So I have some common applications of U-substitutions that we often see. So the first one is where we see different powers of x. So what we look for is the higher power of x, and we can see that in the exponent right here, x squared plus x minus 3. And we can also see the lower power of x, 2x plus 1. So that means that we are going to set u equal to the higher power. So u is going to be x squared plus x minus 3. Notice I set it equal to that whole exponent. And we're going to see the purpose of this. So I'm going to skip straight to du dx is equal to 2x plus 1. So does that look a little familiar? Because I hope it does. I'm going to multiply that dx over, so I get du is equal to 2x plus 1 times dx. And finally, I can divide that over. So du divided by 2x plus 1 is equal to dx. So now we have lots of parts in here that we're going to go ahead and fill in. That 2x plus 1 stays the same because we didn't manipulate it at all. But that becomes e to the power of u. And now our dx is equal to du divided by 2x plus 1. So like I said, the purpose of doing this is we want things to cancel out. If things are not canceling out, we might want to switch what we set our u equal to. And that's totally okay. Trial and error is a great way to find what our u is going to be. But now we can go ahead and take the antiderivative of e to the power of u. I don't have any x's here, so we are good to go. So we get e to the u plus c. And our last step is to replace in what u was originally equal to. So x squared plus x minus 3. So if you wanted to check your answer, you would of course take the derivative of that and you would get back to what we were taking the antiderivative of. So that is one common example you see. Here we have another example, and this is typically where you use a denominator. So if we have some kind of quotient, we are going to set u equal to the denominator, 3x squared minus 4. So now I'm going to skip another step, and I'm just going to say du is equal to 6x times dx. I just immediately skipped that step. This is the most common way to write it that I've seen. You can set up every step. That's totally fine. But if you're wanting to maybe save some time on an exam or on homework, you can skip straight to this step. So now I know that dx is going to be equal to du divided by 6x. Let's go ahead and replace these. So first we have the antiderivative of x. That did not change at all, but we set the denominator equal to u. And now we can replace what dx was equal to, which is du divided by 6x. So notice here what cancels out. It's that x right here. And so now we can rewrite this. If you're wondering what to do with that du over 6, we can rewrite this as 1/6 times du. And when we have a scalar, we can just move that scalar to the outside. So let's go ahead and do that. And now we can go ahead and take the antiderivative. So here we get 1/6, and this becomes the natural log of u plus c. Our last step, of course, is to replace u back in. So we get the natural log of 3x squared minus 4 plus some value c. And that's our solution. Again, if you want to check it, you can go ahead and differentiate it. Make sure that we got what we're originally taking the antiderivative of. A third common example I see is when there is a really big power involved. So notice here we have to the power of 10. We don't want to try to FOIL all that out. That would take way too long. So the trick here is to set u equal to what is ever inside that really big power. So here I'm going to set it equal to x squared plus 2x. I'm going to skip some steps, like I said, so I'm just going to say du is equal to 2x plus 2 times dx. Now I can divide that over. I get du divided by 2x plus 2 is equal to dx. So now we can go ahead and replace these in. So that x plus 1 didn't change, but we set the inside of this one equal to u, and we get du divided by 2x plus 2. Notice we do not immediately see what is going to divide out in this case, but that's because we just need to do some algebra. I can pull a 2 out of both of these terms and I get x plus 1. And now we can see these x plus 1's cancel out. And so we have that 2 remaining in the denominator. If you want, you could bring that out as 1/2. And now we have the integral of u to the power of 10 du. So let's go ahead and take the antiderivative of this. That 1/2 hangs out since it's a scalar multiple. We add 1 to the exponent and we divide by that new exponent and then plus c. So if we wanted, we could rewrite that. The u is equal to x squared plus 2x to the power of 11. And in the denominator, now we get 2 times 11, which is 22, plus c. And that right there is our solution. So if you see really big powers, try setting that inside equal to u. Another common example I see are radicals. So like we know, we can rewrite at radicals, and this becomes 3x minus 4 to the power of 1/2 in terms of x. So my suggestion is that we set u equal to whatever is inside the radical, so 3x minus 4. So du is equal to 3 dx, and I'll divide that 3 over, so du divided by 3 equals dx. So let's go ahead and replace these. We have the antiderivative of u to the 1/2 times du divided by 3. So again, like I said earlier, this is just a scalar. So I can move that to the outside. That becomes 1/3. And now we have the antiderivative of u to the 1/2 du. So let's go ahead and take the antiderivative. We get 1/3. We add 1 to the exponent, so that becomes 3/2, and we divide by that new exponent. And we have to add our c value. So I'm going to rewrite it one more time. That 1/3 is hanging out. When we divide by a fraction, we can multiply by the reciprocal of that fraction. So we can just multiply by 2/3. And now we can replace what u is equal to. So 3x minus 4 to the 3/2 plus c. If you wanted to, you could go a step further. So that becomes what? 2/9 3x minus 4 to the 3/2 plus c. I would say the step before, if I were grading, that's 100%. Okay, so another common one is composite functions. So when we have, like in this example, cosine of the natural log of x, so when we have two functions composited together like that, always set u equal to the inside. So u is equal to the natural log of x. That tells me that my du is going to be equal to 1 over x times dx. So what I'm going to go ahead and do is multiply both sides by x. So then this 1 over x cancels with the x, and we get x times du is equal to dx. So let's go ahead and replace these so that cosine doesn't change, and that becomes a u on the inside. We didn't do anything to that x in the denominator, so it still hangs out. And now let's replace dx, and that's x times du. So like I said, there's going to be something that cancels. All the x's have to cancel. If they do not cancel, that just means we need to pick a new u, and that's totally fine, trial and error. So this becomes the cosine of u times du. And that is something we know how to anti-differentiate. So that becomes sine of u plus some constant c. We can replace u back in, and that is sine of the natural log of x plus c. I want to go ahead and check this one to make sure that this is actually our solution. So let's go ahead and take the derivative of that. So here, let's go ahead and use chain rule. So the derivative of sine is equal to cosine. The inside stays the same. And now we multiply by the derivative of the inside. So the derivative of natural log of x is 1 over x. And then that plus c goes to 0. We can rewrite this as cosine of the natural log of x divided by x. If we compare our answers, we have our derivative is equal to what we originally took the antiderivative of. So we know that this is for sure our solution. So like I said, U-substitution is just used as the opposite of chain rule. So these are not going to be the case 100% of the time. They're just very common examples that I do see. So this is all I have for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.